Hi there, I'd like to do a fairly quick lesson on circular motion today. We're going to do a couple of examples. So the first example will be a bit of a loop-the-loop. If you remember having Hot Wheels as a kid, we're going to be looking at something along those lines, but rather than looking at the little Hot Wheels from when you were a kid, we're going to look at something of a bigger scale. So we're looking at something that has a diameter of 40 feet. So I'm looking at a real life-sized car going through a loop-the-loop, and I like to look at some of the mathematics behind making this happen. So is it reasonable? Is it possible? So if we start off with a 40-foot diameter, let's first convert that to a metric measurement. So to do the conversion, I'm looking at, let's see, there's 3.28 feet in 1 meter. So the feet will cancel. And I'm going to take the 40 feet and divide it by the 3.28, and that'll give me about 12.2 meters as my diameter. So 12.2 meter diameter, and so that means, let's see, okay, this is the same thing as 12.2 meters, and that means that the radius is equal to 6.1 meters. Okay. So we've done that. We've converted it over to a metric measurement. Now I want to look at the math involved behind this vehicle actually being able to stay attached to the track. So first off, you're going to take your car, you're going to enter your car into the loop-the-loop, you're going to drive it, and then that car is going to go around the loop-loop, and at some point in time it's going to get to the very top. Now, at the very top, you are not able to get to a velocity of 0. It must still have a velocity off in this direction in order to be able to maintain contact with the loop-the-loop, otherwise with the track. Otherwise, it's just going to fall out right here and fall, and that is not what we would want to happen. So you want to have some sort of minimum amount of contact between the wheel and the track. And in order to do that, it must have a velocity in the direction to the left, and that's what we're going to be focused on. So at the top, we have this equation of acceleration is equal to v squared over r, and we are concerned about what the velocity is along the tangent at the top. Of course, at minimum at the top, the acceleration would be that of 9.8. The point at which the wheels are just about to become detached from the track, the acceleration downward, right? The acceleration downward would be equal to 9.8 at its minimum. So we're going to just rearrange and solve for v. So that means that v is going to be equal to the square root of AR, or if you want, since we're looking at gravity as being that minimum acceleration, I'll change that to a g. So it's the square root of GR. And so that'll give us our minimum velocity along the track. And remember that our track radius is 6.1 meters. So we're looking, I'll just clear that out. So I'm looking at, let's see, 9.8 acceleration of gravity times the 6.1 track. And I always go to this power of 0.5. I find that to be easier and more consistent rather than taking the square root. And so I'm looking at the 7.73 meter per second. Velocity, and that is at the top. That is the velocity at the top. Okay, good. So now what? Now, if you were to do this, you would want to know what velocity you would have to be at the bottom in order to be able to enter the track, and then you would have that velocity at the top. And of course, we're going to use energy considerations to make that happen. So the potential energy at the top, not sure what happened there. So the potential energy at the top plus the kinetic energy at the top. Acting a little funny on me here. equals the potential plus kinetic at the bottom. Of course, there's no potential at the bottom, so I'm just going to do the kinetic energy at the bottom, and then I can go ahead and do my substitutions. So potential energy at the top, I'm looking at mgy, mgy plus 1/2 mv squared. Of course, those are both at the top, and that is going to equal the 1/2 mv squared at the bottom. This is at the top, and that's also at the top. So my position here at the top is 12.2 meters. My velocity at the top here is the 7.73 meters per second, and I want to solve for the velocity at the bottom. Let's see, the mass cancels out all the way across, and I'm solving for that velocity on the bottom. So multiply everything by 2. Oop. No, I was making a mistake there somewhere. Okay, so that's 2gy at the top plus, see, it gets rid of the 1/2, so that gives me the velocity at the top squared. It's going to equal the velocity at the bottom squared. Yeah, and so now lastly, I just take the square root. So the velocity at the bottom is equal to square root of 2gy. Not even sure how that happened. Plus the velocity at the top squared. And just to be consistent about it, might as well put in my numbers. So 2 times 9.8 times the 12.2 plus the 7.73 squared. All right. 2 times 9.8 times 12.2 plus 7.73 squared. And now I can take the square root. And we have an answer of, let's see that again, 17.3. 17.3 meters per second, and that is the velocity at the bottom. So you could take a life-size car to go around a 40-foot loop-to-loop, enter the track at the bottom at 17.3 meters per second. You'd be going about 7.73 meters per second at the top and be able to maintain contact with the track. Now the other question is, what will be the g-forces acting on you throughout different parts of the track? Well, at the top, you'd be undergoing 1g, but not due to the track. That would be just due to gravity. And if we look here, your acceleration is going to be largest when your velocity is at its largest. So since your velocity is at its largest at the bottom, we would have the largest acceleration there. So let's use this 17.73 meters per second in order to determine what the acceleration would be at the bottom. So let's see here. We're going to look at the 17.3. We're going to square it and divide it by the radius of 6.1. And so just about 49 meters per second squared. So you're looking at almost 5 times the acceleration of gravity due to the track when you're at the bottom. But of course, remember that when you're at the bottom, just standing on a track, you're experiencing 1g anyway. So you have 5 g's of acceleration, 5 times the multiple of gravity, just due to the track when you're at the bottom. When you're entering and leaving the track, you'd be pulling 5 g's due to the track, but an additional 1g due to gravity itself. So you would actually be pulling 6 g's. You'd be pulling 6 g's when you're at the bottom. How about that? And of course, we can also convert this to a mile per hour measurement. So if we do that real quickly, let's see, I'll do that over here. So we have the 17.3 meters for every 1 second. I'm going to go from miles, or excuse me, from meters to miles. So let's see, there's 1,609 meters in 1 mile. Meters cancel. And there's 3,600 seconds in 1 hour. So just real quickly, I'm going to take that 17.3. I'm going to take that, I'm going to multiply it by the 3,600 and divide it by the 1,609. So 38.6 miles per hour. So you just kind of consider as to whether that's something that is reasonable and something that you'd even consider doing if you were to build a 40-foot diameter track. Just a little hint, it's been done. My numbers are not fake numbers. They're actually based on a real example. And if you want to go ahead and look it up, look up 5th gear loop-de-loop, and you'll see a couple of stunt guys who did this exact trick. All right, that's it. Now, let's see if I can go over a little something else. Okay, so a totally separate example. I want to look at the example of someone out in space in some sort of space habitat. And so just kind of imagine this thing being some sort of cylindrical, three-dimensional space habitat where a person is standing on the inside of their space habitat. Okay, so they're on the inside of the space habitat here, and the floor is essentially pushing towards the center on them, maintaining their circular path. And we want to look at something like, given that this thing has some sort of size to it, some diameter and radius, how quickly does it need to rotate in whatever direction, left or right, clockwise or counterclockwise? How quickly does it need to rotate in order to simulate gravity? That's what I would like to consider here. So let's kind of make up a diameter that seems reasonable. So let's look at sort of a football field sort of sized space habitat. Semi-realistic, but big, but semi-realistic. So it's let's just kind of say it's a radius of approximately 50 meters, just to kind of give that number. Oops, didn't mean to do that. So 50 meters of a radius. I'm not even going to deal with feet this time. The reason why I dealt with feet the last time was because there was a real world example that I actually knew those numbers on. Like I said, you really should check it out. So 50-meter radius. Okay, so what do we want to consider now? Okay, see if I can pick up the pace here. So we know that the acceleration is equal to v squared over r, and we want to simulate gravity, so the acceleration is going to be 9.8. We can figure out what their velocity along the tangent would be, but what I'm going to do is I'm going to say that the velocity is 2 pi r over t, right? At any point in time, the velocity along the tangent is 2 pi r over t. It's the circumference of the circle divided by the time it takes to make one complete revolution. So that's 2 pi r over t, put that in big parentheses, that's squared, and that's over r. Distribute through, so I'm looking at 4 pi squared, r squared over t squared, and again, that is still over r. So one of the r's will cancel, that in fact is an r, excuse me, and so that's going to simplify down to 4 pi squared r over t squared. And a really important thing that I need to give you is that t is equal to 1 over f, and f is equal to 1 over t. So what is f and t? So t is the time measured in seconds for one complete revolution or rotation. F is the frequency. So while time is measured in fact, I don't even need to put an equal sign. So time is essentially how much time occurs per cycle. So this is seconds per cycle. And this over here is going to be cycles per second. Those are essentially units. The cycle isn't really a unit per se. It's more of a placeholder, but regardless. All right, so with that stated, can move that off to the side. And so with that statement, I can also say that this is equal to 4 pi squared r times f squared. And frankly, what I would like to do, I think would be very often better to, depending on what the numbers are, it might be better to solve for f or t. In this case, with it being so large, if it's going to take multiple seconds for it to go around once, perhaps it's better to solve for t. If it's making several revolutions per second, then solving for f would be more reasonable. It's just more intuitive in that way. I think in this case, it's probably going to take more than 1 second for it to go around to simulate gravity, so I'm going to solve for t. Okay, so a is equal to 4 pi r over t squared. 4 pi squared over t squared, excuse me. So that means that a times t squared, equals 4 pi squared times r. And I want to, again, solve for t. So that means that t is going to equal to a times 4 pi squared times r. I have to take the square root of that. Okay. So let's go ahead and plug in my values where r is equal to 50. 9.8 is my acceleration that I'm trying to achieve, times 4 times pi squared times the 50 meter radius. And I can't imagine, oh, yep, okay, forgot to take square root. I freaked out for a second. Okay, so 130 seconds it would take for one complete revolution, so a little bit more than 2 minutes, actually. Actually seems a little high. It is high. I made a mistake. If you haven't been able to tell, I'm under the weather and tried doing some mental math there that just did not work out well. So let's try this again. So, let's see. A times t squared equals 4 pi squared times r. Divide each side by a. So t squared equals 4 pi squared times r over a. For some reason I multiplied it by a, and now I need to take the square root. So t is equal to 4 pi squared r over a. Take the square root of it, and that seems much more reasonable. Let's try that again. That's embarrassing. 4 times pi squared times the 50 meters divided by 9.8, and take the square root. There we go, 14 seconds. I thought that seemed significantly too high before. So we're looking at 14 seconds for it to go around once, and that seems much more of a reasonable answer, which is why it's always good to kind of just really consider your numbers before moving on. So 14 seconds, and of course, 1 over 14 would give you how many cycles per second. So it'd be obviously a fractional value. Okay, so a couple of examples there on applying basically this equation, and that's what I wanted to go over. Okay, thanks.